Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start the lecture number 17, and in this lecture we will cover Boolean and comparison instructions. So before starting this lecture, we will review what we did in lecture number 16. So in lecture number 16 we discuss about procedures, how we can create procedures and how we can document procedures. Like to create procedure, there were some instructions or the directives like procedure name, and we use the directory procedure option, and then the procedure name and the NP or end procedure. And to document procedure, we already discussed that we have to write the comments, that what will be the input, what will be the output, or what are the requirements for the procedure. So we have to mention, we have to document everything inside the procedure, the purpose of the procedure, for what purpose this procedure will be used, and when a new another programmer they want to use these procedures, they can easily get this information, the function and the registers which are being used by these procedures. So it's better writing a skill to write the procedures. You can call it a better programming skill when you are programming in assembly or in any other language. And then we did one example of sum of procedure. We use the two registers and their sum, three registers, and their sum was in EAX register. Call and return instructions, we discussed call and return instructions very briefly. Call instruction, we saw that this instruction was used to call the procedure. So the syntax of that call instruction is like we use call and the procedure name here. So the call instruction will call this procedure. Along with calling, what will happen, the instruction pointer or a register or the next instruction that is to be executed, it is being stored in the stack. And on the contrary, return instruction returns from the procedure, and this return instruction is inside the procedure. When this return instruction executes, what will happen, the instruction pointer that was set or saved inside the stack, it has been popped and recalled, so that the program continues its execution from the point where it has resumed, where it has break the normal execution. So call instruction is in the main body of the program, and return instruction is inside the procedure. We also discussed the nested procedure calls. How we can use nested procedure means we are calling one procedure from another procedure, and from the next procedure we are calling third procedure, and so on. And we saw that when we are calling procedure 1, then its instruction pointer or the address is being stored inside the stack for the procedure 1, and if we are calling second procedure and third procedure being called, then the second procedure's instruction pointer is also stored. So stack is being used to store all these addresses to when we return from these nested calling or nested procedures. So again our program resume its execution from where it was break. We saw also for the local, we discussed about local and global labels. The local labels are defined inside the procedures, and we can access them within the procedure. Global procedures are defined in the main program or the main body of the program, and they are global. Their scope is at the global level. Even procedures can also use those calls or these labels and transfer control to those labels. We also saw some flowchart symbols, how we can write the flowchart for the procedures that we are writing, we are using in our program. And then last option that we discussed, or the last operator that we discussed, was uses operator. This uses operator defines that what parameters or what are the registers that are being used inside the procedure, and these registers are pushed inside the stack when procedure executes, and popped when they are automatically popped when they are when the procedure completes its execution. We discussed most of these topics like nested procedure calls, local and global labels, and also the uses operator, but we did not program them. We did not saw their examples in assembly language. So inshallah today we will do all those examples during this lecture, along with the other coding or other examples that we will discuss in the lecture. So what we will discuss in the lecture are the Boolean and comparison instructions. So as we know that Boolean and comparison instructions are used to manipulate the bits, and these are the they manipulate the bits of these registers or the operands, and they will affect the flag registers, flags inside the flag registers. So what we will discuss in this lecture, first we will discuss about the CPU status flags. We will review because we already discussed about these flag registers. Flag register and its main flags like auxiliary carry, sign, 0, and other flags. Then we will discuss about the AND instruction. This is the Boolean operation. AND instruction, what is the operation of this AND instruction, what is the syntax, and what is the purpose, for what purpose we can use this instruction. Simply all these instructions are like very simple instruction, but they have a very significant importance, or they are very significant, so that we will see in different examples. Then next instruction that we will discuss is OR, then exclusive OR, NOT instruction, and so on, and we will see their applications by analyzing their use in different examples. Then test instruction. This test instruction is a comparison instruction that will compare two operands, and then compare instruction. So these two are the comparison instructions. We will see what is their purpose and what is their use. So this is the outline of this lecture. Now first of all we will review the flags. So first flag is a 0 flag, and we know that this flag is set when the result of an operation is equal to 0. For example, if we subtract or add or do something, if we subtract or add or perform any other operation, if the result is 0, then this flag is set. On the contrary, if the result is different, either negative or positive, whatsoever the value is, this will be reset in case if it is already set. Then we have the carry flag. Carry flag is set when the instruction generates the result that is too large or too small for the destination operand. So in this case the carry flag is set. And the next is the sign flag. We know that the sign flag is set if the destination operand is negative. For example, if we perform some operation and the destination operation or the operation generates a result that is negative, so the sign bit is the most significant bit. If it is set, it is being copied or it is being moved to this flag. So the negative or that bit is also same as the flag bit, sign flag bit. This bit is cleared if the destination operand is positive, because if the result is positive, then definitely the sign bit will be 0. On the other hand, there are different other flag registers, and the important one, overflow flag. So overflow flag is set when an instruction generates an invalid signed result. So in case this overflow flag will generate this overflow flag will be set. There is another one is called the parity flag. This parity flag is set when an instruction generates an even number of ones. For example, if the result has the even number of ones, like here you can see, if we have 0, 1, 0, 1, 1, 1, 0, 0, and so on. So if this is the output, then the number of ones are even, so it means this flag will be set. On the other hand, if there are odd numbers, then it will be 0, and so on. Then we have auxiliary carry. This auxiliary carry flag is set when an operation produces a carry out from the third bit to bit number 4. So it is a carry when we borrow, or when carry happens from third bit to the fourth bit, and so on. So in this case, this auxiliary carry flag will be set. Now first instruction that we will that the Boolean instruction is called the AND instruction. Here you can see this is a truth table for the AND operation. If we have Boolean value like two variables x and y, and this is a sign for AND Boolean operation. So if x and y both are 0, if we perform AND, result will be 0. And if it is 0 and 1, then result will be 0. If it is 1 0, then it will be 0. And for 1 1, it will be 1. This is very easy, just to recall the concept of AND or the Boolean operations. So when all these bits, for example, these two bits which we are comparing, they are not similar, then they are not 1, for example, the result will not be 1. If both are 1, then result will be 1. If any of the bit is either 0, then the output will be 0. So you can see all this here inside this truth table. So this AND instruction, it performs a Boolean AND operation between each pair of matching bits in two operands. So there are two operands that are involved, and these operands, this source can be any register, any constant or something whatsoever, and the destination register, destination is can be a register. It cannot be a constant, so it can be a register or whatsoever. So it will perform, AND instruction will perform comparison or AND operation between these two, but it will perform in bit by bit pair operation. Here you can see, for example, our source is this one and destination is this one, for example. Then what will happen? So if source is like 0 0 1 1 1 0 and 1 1, so 1 is ended with the next one, so result is 1, and so on. Here it is 0 and this one is 1, so this will be 0, as you can see in the truth table, like this one. Similarly for other, all this one, everything is like 0 0, because we are going to end with 0. Here you can see, if we want to clear any number of bits, for example, if we want to clear bit number 0, bit number 4th to 7th bit, 4th and 7th bit, 4th to 7th bit, from 0 to 3rd bit, we want to make them unchanged as it is. If you can see here, these 4 bits, we want to make them as it is. We do not want to do anything. We want to keep them unchanged. So we write all these ones that we are going to compare here. All these are ones. So all these bits in this operand, they will be same as it is. If we want to clear these bits, whatsoever their values are here, either zeros or ones, they will be reset. So this is very simple operation, AND operation, and then we will move towards the next operation, that is called the OR operation, and the instruction name is OR instruction. This there is a truth table for the OR operation. You can see here, if any of the bit is 1, if any of the bit is 1, if we compare a pair of bits, so here you can see, if this bit is 1, here this bit is 1, and even though if two bits are 1, the output will be 1, and the output can be 0 only in the case when these two bits or the pair has all zeros. Here you can see the syntax. So this is OR operation or OR instruction. There is source and destination here, destination and source. So if we compare R, what will happen? So if we want to set all these bits from bit number 0 to bit number 7, if we want to set all these 4 bits, and if we want to keep them unchanged, then put all these zeros and all these ones. So these bits, all bits will be set, and these bits are these 4 bits will be unchanged, or they will be as it is. So what we can write here, for example, if we write all these ones that we are going to compare with these bit number 0 to bit number 3, they will be set, and all these bits will be unset or unchanged. the exclusive OR operation or exclusive OR instruction. This exclusive OR instruction, here you can see the truth table. For the exclusive OR, the sign that is being used is like a circle, and there is a positive inside the circle. Here you can see in this truth table there is 0, x Boolean variable is x and y. These are two Boolean variables. If x is equal 0 and y is equal 0, result will be 0. And if both are 1s, result will all again be 0. However, if they are different, if x and y, they are different, either x is 0 and y is 1, or x is 1, y is 0, the output or the result of this exclusive OR will be 1. So this is most important instruction. We will use this instruction mostly. This operation is mostly performed in different operations or different applications. For example, in cryptography, or when we perform some operation to hide information, then we use exclusive OR. So maybe in the advanced subjects, when you will study all those subjects, you will use this exclusive OR. So here the syntax for this exclusive OR is almost similar, and here you can see, if we want to invert these 4 bits, invert means change them. If they are 0, we make them 1. If they are 1, we make them 0. If we want to invert them, then we will use this mask or this bit pattern, all these ones. So this whole portion of this operand will become inverted, and if we want to make them unchanged or keep the same number of bits, then we will use 0, 0, 0 and so on. So you can see, if this 1 and 1, they are exclusive OR, definitely if they are same, it will be 0, and if these 2 bits are same, then it will be 0 and so on. If they are not same, or they are different, as dissimilar, then it will produce result 1. And on the other hand, similarly, you can see bit number 3 is also same, so it will also give you the it will invert the bits in the destination. Now here you can see all these bits are like 0, 0 and 1, 1, but here the exclusive OR operation is being performed with the bit pattern that is all zeros, so it will remain same as it is. What will happen, because here is 0 and here is 1, whatsoever, either here on the upper hand side, if whatsoever the bit pattern is, it will remain as it is. For example, if we say 0 and 1, they are being exclusive OR, it will be 1, 0 and 1, there will be 1. For 0 and 0, we know that 0 and 0, if they are similar, even the output will be 0. So this is also used to perform this operation in some applications, like if we want to hide some information. So we will have some bit pattern, we want to compare, we want to exclusive OR that bit pattern with the information, and we will receive some different information that is not similar. So if we, here you can see, if we again exclusive OR, so this was, for example, a key. If we again exclusive OR with this one, the same one, 0, 0, 0, 0, 1, 1, 1, 1, the result will be again the same result. Here you can see 0, here is 1 and 0. If we exclusive OR, it will be 1, 1 and 0, it will be 1, 1, 1, it will be 0, 1, 0, it will be 1, and 1, 1, 0 unchanged. So you can see the output, if we again perform exclusive OR with the same bit pattern, so we will receive the same output. So for example, this is the scrambled information, we scramble this one, nobody can understand what is the original message here or original information, but if we again exclusive OR with the same bit pattern, we will receive the same result or the original information. I will not discuss in more detail, like in the cryptography or other applications. We use exclusive OR. Even for masking, for masking we use this mask bits and so on. So this exclusive OR, as I told you, is useful to toggle or invert the bits and operand and so on. So here NOT operation, this NOT operation inverts the actual or the original operation or destination operand, whatsoever the operand is. So it inverts. For example, if X Boolean variable is true or false, or it is 0, then it will be inverted, it will be 1 or true. If Boolean variable X is 1 or it is true, it will become false or it will become 0. So we are inverting by using this NOT operation. So NOT operation performs a Boolean NOT operation. This NOT instruction performs the Boolean NOT operation on a single destination operand. As you can see here, we don't have any source operand, and so we don't have any source, only destination. So operation will be performed, and again the result will be stored in the same destination operand. And here you can see we are going to perform NOT operation on this bit pattern, bit number 0 to bit number 7, for example. So if it is 0 0 1 1 1 0 and 1 1, it will be inverted. So you can see the inversion. Zeros are converted to the 1 and 1s are inverted, and the result is also result is 0. So for this 1 we invert it to 0, this 1 is 0, 0 is 1, and so on. So these are very simple operations. Now we will discuss their applications. For example, we discuss AND, OR, exclusive OR, NOT, and so on. What are their applications? For example, if somebody asks you to convert the upper or the character in AL to uppercase. So for example, A is a character. We want to convert this A into the uppercase. We know that the ASCII table. So ASCII, American Standard Code for Information Interchange, is 7-bit code to represent 2 power 7 characters. So ASCII code for A is actually is 1 1 0 0 0 0 and 1. So it's like 1 2 3 4 5 6 and 7 bits. Sometimes people write here like 0 so to make it like 8-bit, but if it is 0, it's okay, no problem. So if you want to make it like this one, it's okay. If you want to present in 7 bits, it will remain same. Now what will happen here, the difference between A and small a and capital A is only this bit is different. These 4 bits are almost similar, actually the 5 bits, but we divide them into like these three most significant bits and the 4 least significant bits. So they are almost similar, only the 6th number bit, the 5th number bit here is different. Bit number 1 is different. So what we want to do, if we want to convert or invert this bit or reset this bit, so we can use AND operation. How we can use AND operation? For example, you know that if we AND this one, the value is like here, 1 1 0 0 0 4 zeros and 1. I want to reset this bit, so I will put it like 0, and all the other bits are 1 1. So if I perform AND operation, and we know that AND operation will return the value like this one. So this one will be 1 1, it will be 1, they will be unchanged, all these will be unchanged. Here they will be unchanged, only this bit will be reset, or it will be like, if it is 1, then it will become, if it is already 1, then it will become 0, and the rest will become same. So now this code is for this ASCII code is for the capital A. So we use AND instruction to clear the bit number 5, and here you can see, for example, if we use move AL comma A comma the character A, so AL will be equal to like this one. If it is in hexadecimal, then you will see like this one, it will be 1. So 61 will be for the A. 61, yeah, it will be okay, 61 for the A, and then when you will convert it, when you will perform AND operation, AND AL, so the new value will be inside this one, so it will be 41 or something in hexadecimal. 41 in hex, not in, so this one is in hex, not in decimal, so I just use hex or H to show that these values are in hexadecimal. So 41 in hexadecimal will be for the capital A. Okay, so this one will be 41 in hexadecimal. So this is one application. Yeah, like we know the bit pattern for the ASCII table. If you, I think last time in previous lecture we saw the whole ASCII table. Some bits are almost similar, like the lower order bits, 4 bits are similar for the A, B, C, D, and E, up to all these characters. Only the upper bits are changing, so this is the only difference. Otherwise, almost they are similar for capital and small a, capital B and small b, and the capital C and so on, and small c and so on. And so this is one application. For example, now if we want to convert, there's the next application we want to discuss here. If we want to convert a binary decimal byte into its equivalent ASCII decimal digit. Now, for example, binary decimal byte is, if we assign 6 into the AL register, and we know that 6 is decimal 6 is represented like this one. It will be 0, 0, 0, 0, 1, 1, and 0. So this is binary decimal byte. So we use decimal number to show them in binary. Now we want to convert them to the ASCII. Now you can see for ASCII conversion, actually as I shown here 0 and 1 and 2 and so on, there are these 4 bits are almost similar, like 1 1 0 0, so all these 4 bits are same for all the digits. Only these lower order 4 bits they are changing, like for 1 it will be 0 0 0 1, and for 0 it will be all zeros, for 2 it will be 0 1 0, and for 3 similarly it will be 1 1 and so on. So for the 6, this bit pattern should be like this one, 0 0 1 1 0 1 1 0. Now in AL we have the binary representation for the decimal number. For example, we move 6 in decimal, we want to move it in AL, then it will be in binary. So now what we are going to do, we are going to perform OR operation to set bit number 4 and 5, because this is bit number 4 and 5, 0 1 2 3, and bit number 4, bit number 5, and then bit number 6 and 7. So bit number 4 and 5, if we change these 2 bits, then definitely they will be equivalent to the ASCII decimal digit. ASCII decimal digit. So what we do, we are going to perform, we are going to set these bits. We are not going to reset, we are going to set whatsoever their previous value is, we want to set them. So we perform OR operation, and if we perform OR operation, these bits will be unchanged whatsoever their previous value is, but these 2 bits, bit number 4 and bit number 5, they will be set, they will be 1 1. So the result in the AL will be like this one, and this is equivalent to the ASCII. So we want to set these 2 bits. Definitely this OR operation will set these 2 bits, and the result will be in the AL, and result will be this ASCII value. This ASCII value you can see here is similar to the to this one, which is in the ASCII for the digit 6. Now the third application, for example, now this in this application there is, for example, one instruction that is called the JZ, or jump if result is 0, or jump if zero flag is set. Jump if zero flag is set. We will cover this instruction in the next lecture, but we know already there is a jump instruction, JMP, and we also discussed about the loop instruction. So jump instruction was unconditional jump, means without any condition, but here this jump instruction will jump to this label if the zero flag is set. If the zero flag is set, so JZ is a jump if zero flag is set. So what we are going to do, we want to write application that jump to the label if an integer is even, for example, if the integer is even. So how we can know that integer is even or integer is odd? What we are going to do, the solution is we perform AND operation. So all these integers, whatsoever the integer is, if this last bit or the bit number 0, bit number 1, bit number 2, 3, 4, 5 and up to 7 bits, whatsoever the value is, if this bit is 1, for example, it is odd number. If this bit is 1, for example, if we are talking about the unsigned numbers, if this bit is odd or this bit is 1, then it means the value is odd. If this bit is 0, then value is even. So what we are going to do, we are going to perform AND operation, the lowest bit with 1. If the result is 0, then the number was even. If result is not 0, then definitely number was the odd number. So what we do, here you can see, whatsoever the value is, word value is, we are going to move this value to the AX, and for example, just assume that we are going to assume that the value inside this word val has the value equivalent to like 0, 0, 0, 0, 1, 0, 1, 1 and 0, for example. Okay, so this is the value. So this will be 16, or if I want to make it more simple, so this will be like 6. If this is 6, so we want to move this value to AX. So this AX means it is 16 bits, so assume that there are some more bits here. So the value 6 has been transferred or moved to AX. So AX is like all these bit patterns. Now we want to perform AND operation. AND operation is being performed. What we are going to perform AND operation, like all these 0 zeros, and then 0, 0, 0 and 1. So definitely this will return the value, all these will be 0. So all these bits will be 0 because this bit is already 0. If we perform AND operation, it will be 0. Whatsoever the rest, the combination of bits is, or whatsoever they're either 0 or 1, because here all of them they are 0, so it will be 0. Now the result is 0, and this result will be saved in the AX, and our sign flag, the 0 flag will be 1, 0 flag will be set, so it will perform jump. So if this is even value, in case of odd, if it is odd, for example, the odd value, for example, assume that odd value is 0, 0, 0, 0, 1, 1, 1. So this value is 7. If we perform AND operation for like this one with the 1, so its value will be 1. So we are performing 1 here, and this one is 7. If we perform AND operation, then value or the operation result will be 0, 0, all these zeros, and here it will be 1. So the value is not 0, and AX will be assigned with value 1 and so on. So this is the value you got from this result, and definitely this result is not 0, so jump instruction will not execute, or it will not be performed. So this is the reason we can use all these instructions and all these operations to test either the value is 0, even or odd, so we can test them in our program. Okay, so the The next instruction or next application is if we want to perform jump to a label if the value in the AL is not 0. Now if the value is in the AL is not 0, for example, how we can test? AL can have any value, but if we want to perform the test inside our program that either the value inside AL is 0 or not 0, how we can perform? The reason is the operation is that we perform OR operation or the byte itself. So the byte with itself, then we use the jump NZ. Actually this is the NZ not 0 is when we perform this jump if the 0 flag is not set, if the result is not 0. In the previous example you saw, if the result is 0 or this 0 flag is set, then it performs jump. This JNZ, we will also discuss this one in the next lecture. All these jump instructions in lecture number 18, we'll discuss them in more detail. So this jump will be performed if the value inside AL is 0. Now what about the OR instruction? If you perform OR with itself, for example, OR has the value 0, 0, all these zeros and 1 and so on, for example. If you OR itself, the value itself, the result will be same. So result will be the same value. So AL will be assigned with the same value. The same value will assign to the AL. How we can test? For example, if already value inside AL is 0, 0 and we perform OR with 0, 0, result will be 0. So this will be the new value that will be assigned to this to the AL register. So this jump will be performed to any label if OR has no 0 value, it has some other value. So in case of this one, 0 flag will not be set. The 0 flag will be 0, and in this case the 0 flag will be 1. So what will happen in this case? Jump will be performed if the value is inside AL register is already 0, then no jump instruction will be executed. So this jump instruction will not be executed and so on. So here you can see if we perform OR, as I told you, if we perform OR operation on any number with itself, it doesn't change the value at all. So value remains same, but the flag register is affected. So that is the reason we use this OR operation. Now there are two instructions: comparison instruction, test, and compare instruction. First instruction is test instruction. This instruction performs. This is a non-destructive instruction. It performs non-destructive AND operation, means it will perform AND operation, but the destination register or destination will not be modified. There will be no effect on the destination register. AND or exclusive OR and the other instructions, they perform operation and the result is moved towards the destination register. When we are talking about this test instruction, it will not move or it will not change the destination register, but it will perform the operation, and even the flag register is also changed. There will be some change inside the flag register. So this is called the non-destructive, or it will perform non-destructive AND operation. Here you can see this will perform non-destructive AND operation between each pair of matching bits in two operands. So there will be source operand and destination. This example, there is AL and here some value. So no operands will be modified, either source or destination, but only 0 flag is affected. So the flag register or the sum flags are affected, but not the source and destination operands. In previous instructions like AND, OR, and exclusive OR, and all these instructions, they perform operation and also affect the registers. This is different. So here we perform, for example, if we want to perform jump to a label, if either bit 0 or bit 1 in AL is set. If either bit 0 or bit 1 in AL is set. So how we can see, for example, we are not concerned with all the other bits. If these two bits are, if this bit 0 or this bit 1 is set, it means it can be 0 1 1 0 and so on. So in this case we will perform AND operation. If they are set, if any of the bit is set, then the jump will be performed. How it will be performed, here you can see. So all these bits are 0 and these two bits are only set, so we will perform AND operation between these two. So there will be AND operation between these two, and definitely if any of the bit is set from this either bit 0 or bit 1, even if these two bits are set, for example, the result will be non-zero. Result will be non-zero. So it means it will perform jump if the result is not 0. How it will happen? So here assume that the value in AL value is 0 1 0 1 0 0 1 1 0. So these are like, so remove this for example, and we have this value, and we are going to perform AND operation. So here it will perform AND operation, and definitely all these bits will be 0, and only if we see these two bits it will be 1 and 0. So this value will be transferred, will not be transferred in AL, but it will affect the flag register. So if the result is not 0, then 0 flag is reset, or 0 flag will be 0. So if we see jump 0 to this label, jump 0 to this label, so in this situation it will jump to some this label wheresoever this label has been defined. On the other hand, if the value inside the AL is equal to 0 1 0 1 1 1 and 0 0, for example, what will happen? If we perform AND operation with this, all these bits are 0 except this bit 0 and 1, result will be all zeros. So 0 flag will be 1, but it will not change the value of AL. So 0 flag will be 1, then this jump will not be performed. However, if you use the jump JZ to see that either 0 flag is set or not, so in this case this jump, if you use JZ or jump when 0, jump if 0, then it will perform jump. Otherwise in this case J and Z will not perform any jump to any label and so on. So you saw that this is test instruction, and this test instruction has its own so here you can see this example. So if these bits are, if you use JZ, then jump will be performed. So now we will discuss about the comparison instruction. This comparison instruction does not modify any source or destination registers or operands. It compares the destination operand to the source operand. It's also non-destructive subtract of source from the destination. So destination operand is not changed. Here again you can see here destination operand is not changed. So what will happen here? Source will be subtracted from the destination. We have destination here and we have source here. So source is subtracted from the destination. What will happen? We know that the subtraction. So we have two operands, source and we have destination. What we compare here, as we know that if we subtract source and destination, if the values are same, what will happen? If AL, for example, is assigned 5, if we compare AL with 5, we know that 0 flag will be set, because the result will be 0. If we subtract 5 from 5, the result will be 0 and so on. So this is 1, and the next is, for example, if the destination is less than the source, if the destination is less than the source, for example, destination value is less than the source, so AL is assigned value with 5 or 4, and we are subtracting 5 from the value 4, So the carry flag will be set. And as we know that the carry flag will be set, or carry will serve as a borrow, so this flag will be set, and there'll be no change in the AL. So now we will move toward the next example. What is inside this next example? Here you can see if the destination is greater than the source, so both this carry and zero flag will be clear. Whatsoever the previous value is, zero flag will be 0 and carry flag will also be 0 if we perform subtraction. So there is no borrow here and result is even not 0. So these two flags will be reset, or they will become clear, or they will be cleared. Okay, so here this is the third application of this third operation of this comparison, or how it will give you the results. Then so the comparison shown here is powered with the signed integers. Previously we were using unsigned integers. In case if we use signed integers, for example, if the destination is greater than the source, for example here AL is 5, assigned with 5, and we are comparing with the -2. So whatsoever the sign flag is value, its value will be copied with the, it will be the overflow flag, as we saw in our previous lectures. If the value, we are subtracting -2 from the 5, subtracting -2 from the 5, so sign flag will be equal to the overflow flag. And the next example, if the destination is less than the source, -5, -1 is assigned to AL, and we are going to compare with the 5. So -5, -1 is here, and we are going to perform -5. So sign flag will not be equal to the overflow flag, and so on. Now we will see the examples that we discussed here, and we will test them, use them, all those operations inside the assembly language, and test either they work accordingly or not. So first of all, we will create a project, a new project, and test our previous examples, like in the procedures. So we want to have new directory. We have lecture number 17 here. So we want to create an empty project. Name of this empty project is lecture. Okay. So here we will see, we will add the new item and from the previous lecture. Sorry, here we will say existing item, for example, from lecture number 16, and here was the array example, for example. So in this array example, we just copy this one and add whatsoever the name is you assign them, and we say example 1701.asm. So just be careful, if you select anyone here, or like C++, and if you omit this ASM, then this will be a C++ program. So here you saw this program. We were trying to sum all these arrays. For example, if we take the nested calls, or before that one we will use the before that one, we will try to have an example. That example will perform only the uses operation. So here in the array sum example, we will perform this array sum example, and uses operation will be tested here. So for example, if I want to delete everything here and to show you that this is our program. So this was the procedure. We have used this. If we recall, the total will be used in EAX accumulator register, and here we are using EAX register and also EDI. EDI is the offset address. EDI is the offset address of array W, and next is the length of the array is in the ECX. So ECX has the length of the array, and ECX will be used in the loop instruction, and EDI has the offset address, and ESI has the type of this one. So we are going to perform this addition. We are going to execute this one. So this array sum procedure, first we will test this one, either it works or not. So we just build this one. Okay, sorry, we have to include these files, include directives. So just properties, and here include path masm32, and the directories include directory. So now we just perform this. So it is successful now. So we just perform this one, execute. So first instruction is EDI will be assigned the offset address of this array, and then the length of array will be in the ECX, and the type will be in the ESI. So here you can see ESI is equal to 4 because this is double word and so on. Now we are going to call array sum. So the array sum example is going to produce this result. Here you can see the result of this array sum. We are going to add all these elements. The elements are like these elements here, if you can see them. So 0 0 0 1 and 1 0 and 1 0 0 and 1 0 0 0. So if we sum them in hexadecimal, these are in hexadecimal. So this will be the hexadecimal result. Hexadecimal. If I want to use other variables, maybe it is confusing. To make it more clear, if I want to make them 2, sorry, this should be 1, this should be 2, and this should be 3, and this should be 4. What will happen? This should be 4, sorry. Okay, so if I just build this one and execute, I don't want to go in step by step, so I just, sorry. Here you can see now when I call this array sum, so result is 4 3 2 1 because we are adding these hexadecimal numbers like 1 and 2 0 and 3 0 and 4 0. So result will be 4 1 2 3 4 and all these zeros at the left side from the right to left. So this was example. Now if I use the uses operator, what will happen if I use the uses operator? For example, here procedure uses. Now which registers do we are using here? For example, we use ECX space EDI ESI. These are the registers that we use inside this array. First we build and run this one, and here you will see we are the values of these variable registers, like these are the registers here, ECX, EDI and ESI, their values, they will be preserved again. So before going to execute this one, we will note down the values. So first value in the EDI has the value 9 4 4 and 3 zeros, and ECX is definitely is 4, length of 4 elements, and this ESI. So ESI and ECX has value 44 hexadecimal, and about this EDI is 944. Okay, so now we are going to call this array sum. After calling, even then you can see the EDI value of EDI is still same, ESI is still same, and ECX is still same. There's no modification, and these three registers have been pushed. If you want to see either they have been pushed or not, so we just right click here and see that, go to disassembly and just come to the procedure. So array sum procedure starts from here, and we use this directive, uses directive. At this point you can see there's a push operation before going to execute the first instruction of this register or this procedure. The name of the procedure, the first instruction was move EAX0. Here we perform push ECX, push EDI, and push ESI. So there are three push operations. Whatsoever the list will go here, all these operands will be, or parameters will be pushed inside the stack. Okay, what about when we return? Before executing return instruction, the reverse operation will be performed. So first we pop ESI, then EDI, and then ECX. Pop ESI, EDI, and ECX. So this is the reverse operation we already discussed in our previous lecture, that if we perform push and pop, the push will be whatsoever the order of push will be, pop will be its reverse. So uses operand, uses directive, or uses operation, or uses parameter here, whatsoever we are using here, uses directive, saves all these registers even after execution of this procedure call. So we can use these register values somewhere else because we want to preserve them. These values are being transferred because you know that ECX has been decremented here inside this procedure because ECX has been used as a counter, and when this procedure completes its execution, the previous value that was assigned to this ECX has been again restored. So this was example about this uses. Okay, now we are going to move towards another example about the nested procedure calls. So we will just have the nested procedure call. For example, if we want to have I want to copy this one, and I want to have I want to close this project, close the solution, new project. Okay, it's lecture 17 and 02. The same routine. .asm. No, what happened? So for example, C++ here, so ASM 8. Okay, so in this one I just paste the previous code. Sorry, I can open the code here in the lecture number 17. So I can copy and paste it here. So I just copied and pasted the same whatsoever we did in our previous example in the array sum. I will remove everything from here, from data and from the start. Okay, now you can see here we have one procedure here, and this procedure has nothing. but only the previous one. I want to remove this one, and I want to give them pros1 1 pros2. Okay, here is this one, and then I just set the properties. You can save them in Windows when you path variables inside the Windows, so you don't need to put it again and again. Maybe in the next lecture I will set this one. Okay, so here we want to have multiple calls or nested procedures. How we can make nested procedures? For example, here I want to use move AEAX comma 01 or only 1, move ECX comma 02 or 2, and in this procedure, in procedure 1, I want to increment EAX. Okay, increment EAX, simple. Sorry, here it should be procedure 1. So I just copy this procedure 1, and after copying I just paste it here. And here again the name of this one is the procedure 2. It performs again increment. After performing increment, what I do here, I perform add EAX comma ECX and perform return. But before, here I call the procedure 2. So this is call for the procedure 2. This, I just write some comments here, call procedure 2, and this is procedure 2, so it will increment again and return back here, and from here we have to return back here. Okay, here if I just use the call procedure 1, so okay, so this is done here. In this one I just copy this exit process. So exit process is here. You can write null or 0. We will discuss in more detail about this one, but before that one we just see this. Okay, here you can see we don't have any data here, only code. First we move 1 in EAX, then we move 2 in ECX, then we call procedure 1, and then there's an exit from this program. So this is procedure 1, it starts from here. So this is procedure 1, and then we have also procedure 2, so I just copy this one and put it here. So we have procedure 2 here. So we are calling procedure 2 from procedure 1. I just save this one, and then we just build. Okay, so this build is successful. What will happen? First instruction will be executed here in move EAX. Okay, so 0, ECX is 2. Now we are calling procedure 1, but I want to make it like some points, breaks here, and the next break is here. Okay, so I moved, and you can see now pointer has been moved to the first increment. So first statement inside the procedure 1. So there is increment, and then there's a call to procedure 2. So now from procedure 1 here, we just came to the procedure 2, its first instruction, then there is again increment. Now we will return back. We return back to the next instruction here, that is the add instruction, EAX and ECX. So it has become 5, and then we will return back. So this is the value 5 inside the 5 value is inside the EAX, and there'll be exit from the program. So here you saw we have used the nested procedure calls. Now how these nested procedure call will affect the stacks. For example, if we perform stacks, if we perform nested procedure calls, then definitely here the addresses are being stored inside the stack. So for example, if I run this program, save, and I just run this program, so here our stack pointer points to this point here. Okay, so I just copy this one, and we just observe the memory, what is happening inside the memory. So I just copy this one. You can go to the debug, Windows, and memory modules. So the memory module 1, so here we observe this one. We don't need values here, so I want to, hide this one up to here, reduce this one. Okay, so it has been reduced a bit more. Okay, now we are going to debug this program. If we debug or disassembly this program, here first instruction is move instruction. Okay, move instruction. Our stacks start from this F8 here in this direction, upward direction. So you can observe that when we call the invoke, this instruction or this address will be pushed first at this 4 byte inside this stack. For this address they will be pushed. So then next instruction that will be executed is the move ECX. It has been executed. Now we are calling. When we call, then these bits will change. So this instruction here is the list or the address of the next instruction or the next address. So I just see here inside here is a 2b 10 c2 and 00, 2b 10 c2 and 00. They have been stored here. Now we are inside the procedure, inside this procedure. Okay, so inside this procedure, and inside this procedure we are performing increment EAX. So increment has been performed. Now we are calling another procedure. So after calling, before calling this one, this or when this statement or calling statement will be performed, then this address, because this address is the next address, because we have to return back to this procedure again. So this address again will be stored at these 4 bytes inside this stack here. The address is 3b 10 c2 and 0. You can call it like here this is not the address which will be stored. This is the address there where it will jump. The address will be 00 c2 10 and 38. Okay, just observe these bits. So 38 10 c2 and 00. Okay, 00 c2 10 and 38. So they have been stored inside the stack. Again, when we will come back, instruction pointer is now at this point in the procedure 2. So instruction, we are in procedure 2. So it will perform this execution. When it will return, so this address will be copied inside the instruction pointer. So this has been copied inside the instruction pointer. You can see it is 00 c2 1038. Now it will perform executing this all instructions. When it will exit from the procedure 1 or return, then this one 00 c2 10 will be copied inside the instruction pointer. 00 c2 10 and 2b, they have been copied, and now we are back to this instruction, which is the exit from this process. So this is about the nested procedures. If we call them, each procedure where we exit or where we transfer control, their instructions or their values, their addresses are being stored inside the stacks. Now this is about this one. Now we just close this. We just close the solution. Okay, we don't close the solution, but we can just copy this one and we close solution. We have a new project. 1703. For example, C++ or something, and if I assign lecture 1703.asm, and if I add, it will be assembly. I just copied this program. I just remove everything from here and only the skeleton. Okay, now this is the skeleton of the program. There's nothing inside, there's nothing in the data at all. So we want to test the operations for the Boolean operations. Okay, so we just hit the properties here. Now we will test all these Boolean operations here inside. So the first operation, Boolean operation, is, for example, if we want to perform ASCII conversion for A from A. So if we say move AL comma A, save. If I just build and run this one, so you can see what is inside this. If this move is performed, this, okay, before this there is 61 here, but I want to clear this one first. Okay, you can see R, I don't want to use right now. Now you will understand why I use exclusive R with the same one. I move the EAX comma 0. So if I use move EX comma 0, then definitely all the contents will be erased. I just build this. So the value inside, I just remove this one, 0, and now 61 is the code in hexadecimal for the small a, and it should be converted to the 41 if we want to convert it to the ASCII for the ASCII code for the capital A. Now if I want to perform like AND AL comma 0 1 0 0 0 0 3 4 5, okay, and 1. So there are 2 4 5 zeros and 1. So this will be the new value inside the AL. It will represent the ASCII for the capital A. We just build this one. Okay, 1 2 3 4 5 6 7 and 8. Okay, so we have to include the man32.include lib okay. So this should be in binary, sorry, this should be in binary, so I just build again. Okay, it should be 1 1 1 2 3 4 in binary. it should be include, not in. So we just build, it's successful. Now we just perform this AND operation. So now you can see it's 61, now it will be 41. So this 41 is for the this 41 is the ASCII code for capital A. So this was operation about the AND operation. Then we will move toward the for the conversion of the so this operation was for AND. Then next operation that we will use is for the OR operation. OR operation we will perform converting the binary decimal digits, decimal number which we use to represent in their ASCII equivalent. So as I told you that the ASCII equivalent, for example, if I write here the move, so this is for, I just comment here and write here that this code was for converting small a to capital A ASCII code. So for the reference purpose here, I want to use the same one, converting decimal 0, binary represented decimal 0 to ASCII code for 0. ASCII code for 0. So I just stop this one, ASCII code for 0, and you can see here. Okay, so how we can do that one? We just perform move AL, for example, comma 0, comma 0, and perform OR operation, or AL comma. So this is L comma 0, sorry, we have right here. Okay, 0 0, and the next bit is 1 1. So this is about the AL and all these zeros in binary. So because we have to reset, we have to set these 2 bits to convert this value, because for binary representation for 0 is, 0 is represented, the value 0 is equivalent to 0 0 0, 0 and 1, so 4 and 4, and its ASCII is equivalent to 0 1 1, 0 0 1 1, and all these zeros and so on. Or if I want to use, I want to use 1 here or 1 here, so this is equivalent to 1. Okay, so we want to convert 1 in decimal, one decimal number 1 in binary representation, and then convert it to the ASCII equivalent code. So this will give you the ASCII equivalent code for this one. So we just run this one. I think it's better we just move this one outside. Okay, so this will be available hopefully, so that you can this code for your experiment, or again you want to make some other examples. Okay, so now here you can see this is 0 0 for the, we reset the contents of AX, we will move 1. So 1 is here for this one, AL is only this option, and if we perform the OR operation, then it will be 3 1. Actually it is 3 1 because here this one is 3 and this one is 1, and they are represented in binary here, and they are represented here in hexadecimal. So it's converted here. This operation is successful. So the next one is if we perform jump. For example, if we want to perform jump conditional jump, or we want to see either the flags are being modified or not. So how can we perform these jump? For example, if I say move, so there's another application for performing AND. Move AL, this one is to perform jump when the integer is even. Okay, when the integer is even. So for example, move AL, I don't want to move any other number, only AL comma 3 for example, and then I perform AND AL. Instead of using AL, I use EAX 3, or for EAX is AX is okay. AX is equal 3 and AX with 1. If you use EAX is no problem, so I've used it in binary or the decimal representation. Then if I'm say jump Z to ABC, for example 1 or LBL1, so I want to define LBL1 here. LBL1 is defined here. So if it is 3, if it is even, then it will perform jump, otherwise it will not perform any jump. So I just save this one and I just build. It's successful. So first this is the move EAX, then this is about the converting it to the decimal number to the ASCII, then AX is equal 03, and has been performed. Now it is a result is equal to 1. It is not even, it will not perform jump, and it will invoke again this one. Okay, so this is jump. It did not perform jump. And if you want to see the flag registers, for example, I want to see the flag registers also. So which flags are being affected? 0 flag will be affected. Sorry, the font size is very large, so some flag register become out of the focus. So here you can see, so parity and 0 flag is 0 when we perform this one, after this one, and then here we performed. Then when we perform jump, then 0 flag is not set, carry flag is not set, 0 is not set, so it will not perform jump. If we use not 0, or for example if I want to use 4 here, then you will see the flags also and also jump, but it will be continuous jump. So I will break it afterward, because again and again it will set the value. Okay, so here is the first, and then this one, perform move AX is equal 4, and we are going to perform AND operation with this one 1. Okay, so here you can see 0 flag is equal 1, 0 flag is set, so it will perform jump. Here it came back here, so it will again perform this condition. It will be 0, so the problem is here it will be infinite, so it will continue, but this is just a test. I can stop this one. Be careful when you use. So we are not modifying, because here we are assigning new value. So if you want to compare, or if you want to check in your program somewhere that either the value is like 0 or even or no odd, so in case of odd you could use not 0, it will perform the odd number, test for the odd numbers and so on. Similarly, if we use the OR operation, if I use OR operation here, and I am using OR operation, for example, first I will just say move AL comma 3 or al comma al. So it will jump if the al comma al means it will perform OR operation. If it is al's value is 0, then 0 flag will be 1. Otherwise, in other cases, al's value will remain same. So jump will not be performed. If I use here, for example, jump not 0, then what will happen? It will perform jump. Jump when al has value 0. Sorry. In this case, it will be not 0. So I just copy build solution. So this will perform jump. This one will perform jump if the value of al is not 0. Definitely here the value of al not 0, and we are using nz not 0. So if I run this one, the 0 flag will not be affected. So here we perform this operation. So 0 flag has been reset here. Move al is equal to 3, and we are performing OR operation. So 0 flag is not been modified. So it will perform jump. So it is, if it is not 0, then it will perform jump, and so on. If I change this value, for example, to 0, then what will happen? If we perform the 0, then definitely 0 flag will be set, and here the condition jump instruction has a condition nz if the 0 flag is not set. So this will be different. If I use this one, then you can see what will happen. It will not jump. Okay, here 0 flag has been set when I perform OR operation, or al comma al, so it will not perform jump and it will exit from the program, and so on. So similarly, there are different other instructions you can see. For example, if I want to save, or maybe I don't want to remove, to keep it as a record. So for the compare, for example, test and compare, if I compare al move al comma for example 3 or 5 or 7, whatsoever you can call it, 7. So if we compare al comma 0 0 0, all these 0 bits, and we compare that, for example, all these 2 bits or any of the 2 bit is 1 or not. When we compare them, what will happen? When we compare them, or if I write here, sorry, before compare we will perform test. So first we move al with the value 7, and if we test all these zeros, 0 0 and 1 1 in binary, so here you will see it will perform the test operation, and after this test it will jump to somewhere else. For example, if any of the 2 bits has been set. If I write 7, or maybe if I use the 32 in decimal, so these 2 bits will the last 2 bits for 32, definitely the value for this 32 is it will be, for example, al is 0. Instead of 32 I write another value, for example 16. So it will be 0 0 1 so 1, so this will be 1 2 4 8 16. So all these 4 bits, these 4 bits, and these 1 2 4 8 and 16. Okay, so these for 16 in binary, if I use 16 in binary, in decimal, their binary equivalent is this one. And if I want to test either, so test is, it will perform AND operation if any of this is set, So it will perform this operation, AND operation. If I save this one, build this one and run, if I run this one, then there is all this one. So AL is equal to 10 and 10 in hexadecimal. This will perform test. So test will not change the value of AL, but it will change the value of this flags. So test will, so that it has performed AND operation, and the value of this should be so we perform AND operation and the value is not equal to 0 because none of this was set. So definitely the answer for this one should be different than the 0. So now what will happen if we use the value, and this AL is equal to, for example, 2 or maybe 3, and we build and run again. When we will come here, so here this 0 flag, previously it was set, so now it's not 0, so it has been modified. So the AND operation has performed the value. The result is not 0, non-zero result. And in case, for example, if it is already set, then definitely 0 flag will always be set. For example, in case of 16, you already saw that the 0 flag was already 1, so it did not make any difference. So here if we use 16, for example, and we build this one, if we run, you can see here the 0 flag is already set. Here the 0 flag is here is reset, and again it has been set. This one will again set this flag, but when it is already set, so no change will happen here. So this is the if we use 3 or 5 or something here, 3, for example, if we use 3, so the main thing will be here that if either 0 or 1 bit is an AL is set, so this will perform jump. If any of the bit is we want to compare that either the bits are set or not. Okay, so this is about the test, and then next one is for the compare. Compare, for example, if we perform move AL comma 5 and compare CMP AL comma 5, they are equal. If they are equal, then 0 flag will be set. So it will perform subtraction. So if I just build this one, and if I run this one, here you can see this is all about this one. So move AL is equal to 3, and this is test, and this one is for the compare. Compare EX is equal to 5, and we are going to compare with 5, so 0 flag is set. Okay. Similarly, in case if it is less than, for example, this one is 4, and we are comparing with the 5, then 2 flags will be affected. One is the carry flag, sorry, only the carry flag will be affected. In case if we just test this one, build solution, only the carry flag, debug, and we just, so you can see this is move at the test, and here's the compare. So carry flag is 1. Okay. If we perform the if destination is greater than the source, then what will happen? If destination is 6 and source is 5, so here you can see this one is 6, so destination is 6 and here source is 5, destination is 6, then both flags, carry and 0 flag, they will be 0. So already they are 0, so there will be no effect. So carry flag is 0 and 0 flag is also 0, so there will be no effect because they are already 0. So this is the way you can use all these instructions, compare, test, and other instructions. As I told you, instead of using move EAX comma 0, if I write exclusive OR EAX comma EAX, so if you exclusive OR same register or same bit pattern with the same other bit pattern, then it will clear because all the bits are similar. If you saw if the 0 is exclusive OR with 0, result will be 0. If you exclusive OR 1 with 1, again result will be 0. So this will clear the contents of any register EAX exclusive OR ECX or EBX comma EBX. So it will clear these two registers. I just run this one on registers. So EAX is 0, EBX is 0. So this is one way you can use them, the exclusive OR and all these Boolean operations and so on. So to write some effective programs or effective logic and so on. During this lecture, we discussed about the examples of the procedures. We also, where we discuss about the nested calls and uses. Then CPU flags have also been in the starting of this lecture. We discussed or reviewed the CPU flags again. We saw about AND instruction, OR instruction, exclusive OR. NOT instruction is very easy. If you perform NOT, it will give you the reverse operation and so on. And we discuss about some application and the two other instruction, comparison instructions like test instruction and the compare instruction. This is end of this lecture, and inshallah hope to see you in lecture number 18. Till next lecture, Allah Hafiz.